Welcome to solverfy.
Okay, in this problem we have a scattering experiment where we have electrons being accelerated through a potential difference and scattering off some lattice at some angles and creating an interference pattern. And this angle is to the first maximum of our interference pattern. So the first thing we're asked to do is we're asked to change this table up and express v as v to the negative 1/2, so 1 over the square root of v. We can do that for all the members of the table. I'm only going to do it for the first and last. Sometimes it actually is useful to be lazy, and this is one of those times. We are also asked to get the sine of theta and get a table for it. We could plot those results and we'd have a fairly straight line. Thus, I'm going to take the first and last elements and use that to compute an approximate of a slope, which we're asked to do. I do that here. So the slope I have is about 0.2857. So from here, we're going to be asked to find d, the lattice spacing, from this information. So let's see where this slope will be useful. So we start from a two-slit interference equation. Since we're looking at the first maximum, we have n equal to 1. So we have d sine theta equals lambda. And since we're solving for d, we can isolate it for later, lambda over sine theta. So we need to know what lambda is. So to do that, we can find the de Broglie wavelength of our electrons. Recall that lambda for de Broglie wavelength is h over root 2me, where e is the energy, the kinetic energy of our particle. And this energy is going to simply be equal to the electric potential energy through this potential difference, which would be 2m charge of the electron times v, the potential difference. Okay? And so we can actually, in one more step, separate out all the constants from the interesting variable. So 2me, all of this is a big constant. And then we have our potential difference to the 1/2 power, negative 1/2 power. So plugging this lambda in to our interference equation, we have a bunch of constants, and then multiplied by v to the negative 1/2 over sine theta. And take a look. This ratio is approximately going to be the slope of what we found in that second table. So numerically, we have Planck's constant, 6.626, e to the negative 34 joule seconds, all over the square root of 2 times the mass of electron, 9.1, e to the negative 34. This is kilograms times the, this is not e, this is a little e, charge of an electron, 1.6, 10 to the negative 19 joules. So this is that big constant. And then we can use our slope that we computed experimentally, 0.2857. And when we plug everything in, this should give us the result for our approximate slit spacing. Just doing a little calculation. Oh, one mistake. This is not to the negative 34. This is to the negative 31. So when all is said and done, I have 3.5 times 10 to the negative 10 meters, or about 1/3 of a nanometer. And this is my result for the slit spacing using the experimental data and a little bit of algebra. Okay, thank you very much.